So one of the really interesting things that we could do with this knowledge now of the stress tensors around dislocations is see how our edge defects and screw dislocations interact with point defects, specifically vacancies and interstitials. This is really critical because it kind of shows a very important concept here, which is that defects, their stress tensors, will affect essentially how vacancies and interstitials and other atoms move and interact with each other. So when we have a vacancy, it's typically characterized by this negative relaxation volume that the vacancy creates. That's only about 1/10 of an atomic volume. For an interstitial, the volume is positive, and the relaxations are outward. And that can be very large, actually, or on the order of an atomic volume. So how do we actually visualize and see this? Well, let's draw our lattice. Let's look at what's happening here, and we can remove a vacancy, or create a vacancy. And you see the atoms will relax back. Change in volume of the vacancy is going to be negative on our lattice. But again, small relaxation back. If I add an interstitial, it is going to create an outward, a positive change in that volume. That will create, again, and that will be quite large, almost an atomic volume. So this volume can interact with the hydrostatic pressure in our system. And the pressure is caused by the stress tensor of our edge or screw defect. So this positive pressure for a vacancy formation, you can see it can go down. So positive internal pressure, and our pressure is going to be a negative value as well, depending on where we're at. So what does this actually mean? It means that it's more likely to form vacancies, or the opposite occurs for interstitials. So interstitials will increase the energy of our system, the energy of formation, whereas vacancies will not. Screw dislocations do not have a P delta V interaction. So that's very, very important here. Hence why interstitials form control atmospheres at our dislocations. So you can actually tease out that we have compressive pressure, positive V naught at the top of our edge dislocation. So positive pressure will be there, and the vacancy that will attract vacancies. Interstitials will be attracted and drawn below. And we can actually see this with a really cool little basically simulation that we've developed here. Let me spell dislocation correctly. And we can see we are seeing essentially interstitials being drawn into the bottom of our edge defect. So because of that pressure being positive there, the tension, and that it's going to be drawn essentially there. So we can see that, we can actually see that being done there. So that's a little cool. So interstitials will be drawn there, vacancies will be drawn to the top of that defect, and we can see that there. All right, see you next time for mechanical forces.